realistic effect in the way that the core acts with diffusing temperatures throughout. We also, in the second simulation, added the Coriolis force. So now I'll go through some of our calculations. So the first set is updating material geometries, and so these are our plots. In the plots that I'm showing, A is going to be the first depth, and then through to F, it's going to be going down further, closer to the inner core. So this one, again, is the density and viscosity changes. The radius was also changed to reflect the radii from that first image that I showed at the beginning. And we did also add a rigid boundary condition to the boundary between the inner core and outer core. So I blew up one of the temperature contour plots just to, I blew up one of the range charts just so that we could see that the range that we got, that one's from the first plot, from plot A, is within the expected temperature ranges of 4,000 to 6,000. You will see it's very small, but in F, we do have the red areas being about 6,000 Kelvin, and so our temperatures are within the range that we're expecting. You can also see that the plumes and wells of heat are in different areas, as we're not expecting to see like a uniform temperature distribution. And so the behavior is showing what we were expecting it to see. So the next one is the temperature distributions in Coriolis force. I blew up two of them first just because I showed the vectors on this one too. So the triangles are the rising fluid and the squares are the sinking fluid. And so like these two areas of higher temperature are kind of like rising up around, and that's what these graphs are trying to show. And then I think the squares on the cooler areas are showing that those areas are sinking down. So to summarize the changes for this one, this is the temperature distribution one, and we did add, for this calculation, we did show a spherical harmonic degree of 2 because it's very easy to spot, as you can tell in A, just those two areas of concentrated temperatures. And so that was more of an arbitrary choice just to demonstrate that this code is capable of doing that now. The Coriolis force is also here. And so the spherical temperature distribution is working as we expected. We are seeing the correct, when we input 2 for the spherical harmonic, it is showing like the correct spherical harmonic. So that part of the code is working right. And then you can also see from the way that it's diffusing throughout and kind of creating these swirling motions within, if you go from A to F, that the random distribution is diffusing the temperature. Something to note about this one though is that the Coriolis force was much higher than the actual Coriolis force in Earth, and the reason was that the inertial forces for this are still much too high, which is in relation to the viscosity. So the significance of this is that we're much closer to our goal model, although we still have a lot of work to do. The calculations themselves did display successful new features within Terra that are going to be helpful for us in the future, such as the temperature input at the core mantle boundary. That was probably the biggest thing that came out of doing this. We did make a lot of progress towards magnetic field reversal modeling, although this is going to be a long project that we're very excited to be starting. So our conclusions is that Terra is computationally adaptable for outer core convection problems. Although more changes are needed for this code, we need to fix the viscosity term so that it's much lower, because if we change the viscosity term, then we're going to be able to give a more accurate term for the Coriolis force. And so these two, when you move the viscosity term lower, the Coriolis force is also going to impact the flow a lot more. So then we also are still needing to add our MHD equations. So I would like to thank Dr. Baumgartner for helping me with the adaptations to this code and also advising me on this project. I'd also like to thank Liberty for funding us at this conference and bringing such a big group. It's been a very exciting time for all of us to come here. And I'd also like to thank Dr. Strasser for helping with the travel organization. Does anybody have any questions?
Questions from the audience?